Begin with our demo of our project, infrared vibration sensitive LED drum and metronome, aka LUDS, light up drum system. We consist of four people: Aaron Holloway, Ajay Norton May, and Elisha Peterman, all of us in electrical engineering, and Malcolm Donaldson in photonics science and engineering. To begin with the project description, it's a simple drum with six reflectance sensor under the drum skin, which detects the vibration during each beat, and it outputs the visual signal with the LCD display, and the LED strip. It has two modes: metronome and sensing. During the metronome mode, the LED strip flashes in a rhythmically using the metronome set by the knob, and in sensing mode, the sensor is enabled and it detects the vibration each during each beat, and it outputs the LED flash to the strip.
So here are our goals. Our key goal is that the LUDs should be able to detect the vibration of each strike, and our other core goals are listed below. And here are our three key specifications. The first one is that the LUD should allow for a maximum of 240 LED flashes per minute while performing in metronome mode. The second one is that the reflectance sensors must be placed between 2.5 and 3 millimeters. Sorry, 0.25. From when I started saying the second specification to now, cut here. Our second specification is that the reflectance sensors must be placed between 0.25 and 3 millimeters below the skin to detect vibrations from any point on the drum skin. While not detecting the drum skin at rest, we were able to achieve this and find that the optimal distance was somewhere between 0.5 and 1 millimeter below the skin. And that the LUDs will be designed to operate using both a AC adapter and a rechargeable battery for a minimum of 2 hours, which we were able to achieve.
Here we have the project block diagram. To the right is the legend that shows each team member and their respective components.
Here we have the overall layout of how the components are going to sit inside the drum. The green line indicates where the LED strip will be placed around the inside perimeter of the drum. The red area indicates where the infrared sensor array will be placed. This figure is looking into the drum from the bottom down.
Okay, here we have the power switch. We'll be using the 840315RNZQ for the LUDS device. It was successfully able to switch between two voltage signals. It's a 3-position 4-pole switch. First position being the AC adapter, second position being off, and third position being the battery.
Here is our optical design, which used six QRE1113 infrared reflectance sensors from Onsen, mounted on a wood piece just below, that was designed so that we could adjust the height to find the exact distance that the sensors would best operate from. And when they work by reflecting the IR light from an IR LED into a phototransistor when the drum skin is deformed. For the optimal configuration, the sensor had to be placed on a circuit with a 33 ohm resistor and a 10 kilo ohm resistor. That the resistance values are specifically designed to allow the sensor to operate at a specific distance.
So here is our component connections to the MCU. We have used MSB 430FR6989. It has one switch and one knob. The switch requires two pins, and the knob also requires two pins, which are connected to the MCU with four modules in total, and the LED strip requires one pin to send the output, 3.3 volts, and a ground pin for it as well. And the interior sensors each uses one pin, so total of six pins, which are also connected to the MCU to receive the output from the sensors.
Here we have the Eagle schematic for the non-inverting op amp. You can see where the two resistors are with their respective values.
Here we have the voltage regulator schematic. This would be in between the two voltage signals that we get from the battery, the adapter and the battery, and between the input of the MCU. Next, here's the voltage inverter circuit. That would be between the output of the buck boost converter that we talked about earlier and an input to the negative VCC of the op amp design.
Here we have the Eagle schematic for the switches, and it shows where the pull-down resistors are located to reduce noise. Same thing for the rotary encoders, but we have pull-up resistors leading up to VCC, pull-down resistors that should lead to two capacitors which filter out any noise from the contacts.
Here we have the schematic of the MCU. So the output voltage of 3.3 volts will be used to power the other components, as you can see on the right of the screen, and the pins connected on the left will be taken as the input and then will be enabled to initialize each of the components, and the Core Composer Studio will be used to program each of these pins.
Next, we have here is the PCB layout, specifically a view from the Eagle software. Now, there are many complications pertaining to the PCB. The manufacturer sent the PCB back without parts assembled, which wasn't what the group intended. Our solution was to send both boards back. However, due to long assembly times, we decided to send one board back to us and leave one with the PCB manufacturer. The lead times for certain components are quite long, so we are waiting to receive said components to microsolder the PC board ourselves. We plan to finish the design with whichever PCB gets to us faster.
Here we have an overview of the different circuit components located within the LUDS. We're taking off the lid, the skin of the drum, so we can take a look at the LEDs and the infrared sensor array that's located inside. Here you can see each of the circuits attached to the sensors. With the PCB, those circuits would be on the PCB, and we just have a few wires running from each sensor to the PCB. Can see that if you place something in front of the sensors, it tells the MCU to activate the LEDs. All six sensors sit on a hexagonal wooden board that we have connected to the drum via four bolts, and we can screw in and out of those bolts to tune the distance the sensors sit from the top. That is the dimming module that is responsible for the colors of the LED strip that is located right underneath the sensors. All the wires of the sensors and most of the components lead to the MCU, which is the brains of the project. Next, we're going to take a look at the rotary encoder. You can see we've soldered some wires to it, which connect to the filter circuit shown early in this presentation. Here you can see the two large brown parts are the 0.01 microfarad capacitors, and then underneath them are the pull up and pull down resistors. Then we took a look at the switch, and those are the pull down resistors for the switch. The switch switches between metronome mode and sensing mode. Here's the LCD display and its circuit. It has a potentiometer, which we can use to adjust the contrast of the LCD display. Here we have the power switch. The power switch has three positions. The first position is powered by that wall outlet. The third position is powered by that battery, and the middle position is the off position. And finally, we're going to take a look at the Here we're demonstrating turning the switch. Finally, we're going to take a look at the amplifier circuit with its two resistors and the ratio of them that creates the amplification. The amplifier's output goes straight to the LEDs. And that is a brief overview of all of the different circuits located within the LUDs.
Here we show a demonstration of LUDS is off and now is being switched to use the battery pack. And the LEDs are quite responsive to the sensors. Here we can see the LUD, us using the dimmer module colors of the LED. And as can be seen when the demonstration, the drummer uses his hand on the side of the LUDs, vibrations or depressions that come from the edges can also be detected, as well as from the very center. And in this video, we can see that the LUDs can actually flash multiple colors at once during performance mode. It was not originally intended to design, but since it seemed to be visually striking, we decided to keep it for performance mode.
Next, we have a demonstration of the metronome starting in frequency mode. Now we're switching on to metronome mode. Start.
Here we have a demonstration of the LCD display. So the sensing mode, and the switch can be used to change to metronome, and the switch can be used again to change back to whatever mode we need it to be, and the knob is used to change the BPM. It can be changed up to a maximum of 240, as you can see, and it can be reduced back down to minimum of 15 beats per minute. And here's our future plans. So the final documentation will be completed by April 25th, and as soon as our PCB arrives, we plan on completing the soldering and adding the components to the PCB, and finishing off other extra work that we have personally left to do in the project.
Thank you for watching. We have been Senior Design Group 10, and this has been the Light Up Drum System, the LUDS.